And I think we're live. Awesome. Good morning, everyone. Thank you for being here with us today. I'm your co-host, Sam Bryce, along with Melissa Mendoza, and welcome to the SciPy Maintainers track. I feel really good about the session because we have a great lineup of open source maintainers, and I'm very excited to get an update on all of the projects. So today we'll be hearing from Robert Nihara, the co-founder of Ray, the distributed machine learning make sure this is working. Co-founder of Ray, the distributed computing platform, and he's here to tell us about the universal API that he's developed for building distributed applications. We also have Henry Schreider from PyBind 11, the maintainer of PyBind 11, and PyBind, as you know, is the most, I would say, seamless C++ binding library in the Python ecosystem. Max Klein will also be joining us from the Jupyter Lab project, and he'll be telling us a bit about some of the progress they've made to make Jupyter Lab a lot more accessible in the past year or so. You all may be familiar with Anna Iserman, and she's a core developer of Matplotlib, the ultimate Python plotting library. She's here to tell us a bit about the refactoring that happened to Matplotlib over the past year or so. And Carlos Cordoba from Spider IDE also is here to tell us about a couple of major changes that they did to Spider over the past year, specifically a few things in the debugger and a few things within the user experience. We also have a joint presentation by Colin Carroll, and Predrag Grubsky. Carroll is a maintainer on RZ, and Predrag is he's actually a co-creator of GraphQL compiler. And what they're actually here to share with us is some of the lessons that they learned from the process of adding typings to their projects, which is something I think a lot of projects would benefit from, or at least a lot of people would benefit from, because the process of actually taking a live active project, and adding typings to it is very complicated. And for grand finale, we have Niels from Pandera here to share with us some ways that you can actually improve your Pandas data science pipelines by adding typings and validations. So the way this session is going to work is each presenter will have 15 minutes to give us a quick update on the project, followed by a brief Q&A. Within that 15 minutes, where you can ask project-specific questions. I would say if there's any questions that come up during the presentation, feel free to add it into the questions app within this AirMeet, and we'll make sure and get to it. If at any point in time a question comes up that you didn't get to ask during that speaker's presentation, just feel free to add it anyways, and we'll actually get to that for a general Q&A towards the end. And yeah, so basically, at the end of all of our talks, we're going to have a 30-minute lunch break. And after the lunch break, we're actually going to start a panel discussion. And so I wanted to remind everyone that we do have a maintainers track channel on Slack. So if you are not currently on that channel, please follow the link and join us. And likewise, the discussion or panel discussion, it should already be within the AirMeet schedule. So if you can find that, go ahead and subscribe to it so you can get a notification whenever it starts. Okay, so let's see. All right. So the reason why, of course, I guess the reason why you actually would want to join the panel. So the panel is an opportunity for you to actually engage with these maintainers a lot more intimately on their projects. Basically, we're going to learn about how they got started in open source, some of the lessons that they've learned from maintaining very large projects, some other perspectives when it comes to open source as paid work and open source in academia, as well as you get to ask them what their communities are like, and what it would take for someone like you to go from a casual contributor to being part of the core team. Again, that discussion is in a separate session. Once we wrap up this session, the panel discussion session should open up roughly 30 minutes or so afterwards. And yeah, we hope to see you all there. We have a lot of our presenters committed to actually being part of that panel, so you'll definitely get your opportunity to ask them some pretty deep questions during that panel. So we hope you definitely can attend. And with that, I will turn it over to Melissa, who's going to go ahead and introduce our speakers, and we can get started.
Thank you, Sam. That was wonderful. And yes, I'm also very excited to be here. So hello, everyone. I'm Melissa. I'm a maintainer for NumPy, and I'm extremely happy to be hearing about these maintainers today. So with that, I think we can start with our presentations. And the first one is from the Ray core team. Please welcome Robert Nishihara, who is going to be talking about scaling Python and machine learning with Ray.
All right. Cool. Thanks so much. And can you confirm that you can see my screen?
Yes.
Okay. Great. Awesome. Well, thank you all so much, and it's really great to be here. So I'm going to talk about Ray, which is an open source project several of us started while we were in the PhD program at UC Berkeley. And to say a little bit about my background, I was doing research in machine learning at Berkeley. We were part of the RISE lab, which is an academic lab. It's the successor to the AMP lab, which was the lab which created Apache Spark. So if you're familiar with Apache Spark for big data, there's a long history of open source there, and we were really in a fantastic environment for thinking about open source distributed systems. And since graduating, we've started a company called AnyScale, which is commercializing Ray. So Ray started at Berkeley with a few grad students, but now it's being developed by a variety of companies, including at AnyScale, as well as individuals at various universities and people across the world. And we've been working on Ray for about 5 years now. It's really come quite a long way past in the past few years. And at this point, we have over 500 contributors from a huge number of companies. We just had our second Ray Summit with talks from 40 or so companies, including all of the companies here about how they're using Ray for pretty impressive use cases. I'll talk about some of these, but ranging from production machine learning platforms to model serving to training machine learning models to reinforcement learning and data processing and more. And just to give a sense of some of the progress in Ray's maturity, we recently hit 1.0. Ant's group here is deploying Ray on over 200,000 CPU cores for applications like recommendations, fraud detection, online learning. Amazon, talked about how they're using Ray to do data processing and really increase the throughput of data processing to over a petabyte per hour while decreasing costs by 90%. And Uber is using Ray to train new machine learning models in an elastic and fault-tolerant way. So that includes both classical machine learning with XGBoost, deep learning with Horvath, and a variety of things like that. But let me back up and say a little bit about just what problem Ray is trying to solve, right? So the core challenge here is that distributed computing is becoming the norm, especially for machine learning. You just have to use a cluster. And I'll talk more about why that's the case. But building distributed applications is hard, right? You have to often be an expert. And that's because in contrast with programming on your laptop, if you're programming on your laptop, you can often just focus on your application logic. But to build a scalable application that's running, say, in the cloud or across hundreds of machines, you typically can't just build your application logic. You also have to build infrastructure to run and distribute the application. So our goal with Ray is really to make distributed computing easy. And that's so developers can reason just about, so ideally, so developers can just reason about their application logic and not think about the infrastructure. And so trying to make it so that if you know how to program on your laptop, then that's enough, right? Then you can take advantage of all the benefits of the cloud or clusters to scale. And just to motivate, why really distributed computing is becoming more and more the norm, here is, especially for machine learning, here is a plot from an OpenAI blog post talking about the increase in compute required to achieve the state-of-the-art machine learning achievements, results. And the increase is pretty astronomical, like something like 35 times every 18 months, if you look at flops. And in contrast with Moore's law, which is doubling every 18 months, you can see there's just a pretty huge gap there. And of course, even that is optimistic because it assumes Moore's law is continuing unabated. But if you look at, of course, it's slowed down. But even if Moore's law had continued unabated, there would still be a huge gap. And I think this figure alone, and the picture doesn't change much if you include GPUs and TPUs and so on, that helps. But I think from this figure, it's pretty clear that there really is no choice but to distribute the computation and to leverage clusters. Now that's for the training side of things, but This is true across the board with serving, inference, data processing, and a variety of applications. So the question then becomes, how do we make distributed computing easier? And let me give an illustration now, talk about what is Ray. There are several different parts to Ray. So the first is, there's the core Ray distributed system. You can think about this almost like, just a way to do parallel and distributed Python. You can take your Python functions, you can execute them asynchronously in a cluster. You can take your Python classes, and you can instantiate them as actors or microservices in your cluster. And I'll give some examples of that. On top of this core system, there's a rich ecosystem of scalable libraries. And some of these are libraries that are natively built on Ray, like Tune for hyperparameter tuning, Ray Serve for deploying your machine learning models. Some of these are third-party libraries that integrate with Ray that you can run on top of Ray, and that includes things like Airflow or XGBoost for training or Horovod for deep learning. You can use the Dask libraries on top of Ray. You can use PyTorch on top of Ray. So here, what Ray is doing is it's letting you distribute the computation across the cluster. And then, of course, underneath this, Ray runs anywhere. You can run Ray on any cloud provider, that's AWS or so on. You can run it on your Kubernetes cluster, and you can run Ray on your laptop, right? So a lot of the way that people initially start using Ray is they pip install it, they start playing around with it on their laptop, they get something working, and then they'll take that same application that they just wrote on their laptop and got working, and run it in the cloud or on Kubernetes. So that's the portability there is a pretty important aspect. So I'm going to start by diving a little bit into the core system here and talk about what is the, this underlying distributed system, what is the API that enables such a rich ecosystem on top. Okay, so let me talk to you about, the low-level Ray API. So here's a bunch of Python functions, or 2 Python functions. The details don't really matter, but we're reading 2 arrays from files, and assuming that they have some arrays and some numerical content, and then adding those values together. And what you can do with Ray is you can add this decorator to your functions. And once you do that, now when I invoke one of these functions, when I call readarray.remote, what that does is it creates a task. It returns immediately, and it kicks off a task that's running in the cluster, which will do the work. It'll read the file and return the result, and that result will be stored as an object in memory in the cluster. And the same will happen, with the second read array task. And because the readarray.remote call returns right away, those 2 tasks will happen in parallel. And then we have this add task, which also gets scheduled somewhere in the cluster. And that might happen on a different machine. And the results of the first 2 tasks are being passed as arguments into the second task by reference. And the data will be shipped under the hood to wherever the add task runs. And then, of course, when you want to retrieve the results, you can call ray.get. So this is a way to take Python functions, which might depend on each other in some DAG, and execute them in parallel in the cluster. And so, these tasks are assumed to be stateless, right? You can recover by retrying. You can rerun things if things fail. But if you're familiar with Dask, this is very similar to the task API in Dask. Now, a really exciting part of Ray is the actor API. So here, this is a Python class. Again, the details don't really matter. It's just a simple counter, which you can increment. And we're instantiating that class and incrementing the value a few times. So what you can do with Ray is you can add this ray.remote decorator. And now when you instantiate this counter object, what that will do is it will create a new process, a new actor process somewhere in your cluster. And that process will have a copy of this counter object. And when you invoke methods, and then you have other processes can have handles, this C object can have a handle to that actor that you've created. And now when you invoke methods on that handle, you call the increment method, that essentially is like an RPC, or it's a message that gets sent to the counter actor and causes that increment method to run. So you can essentially, invoke these remote methods or tasks on this actor or this microservice. And you can have different processes all invoking methods on the same actor. You can create multiple actors for parallelism. And for all these tasks and actors, you can specify scheduling constraints. Like you can say this actor needs 1 GPU or lots of memory or different things like that. And of course, and that gets taken into account in the scheduling and is very important for machine learning and deep learning. So that's really it for the core API. The core API, it's just about taking existing primitives that people use for programming, functions and classes, and kind of translating those into this distributed setting. And it's at this level, it's not introducing any new concepts like data sets or neural networks or anything like that. So again, that's the middle layer. That's this core distributed system, which is this universal framework for distributed computing. Now I want to talk a little bit about the library ecosystem on top of Ray. And this is really where most Ray users spend their time. They're not actually, some of them are using the core system, but most of them, they have some specific problem they want to solve. They want to train neural networks, so they're using a library for training, or they want to do data processing, so they're using a library for data processing. So just to give you one example, here is, this is roughly XGBoost code you would write. This is like taking some XGBoost code for gradient boosted decision trees, and the bold terms are the changes you would make to scale it using Ray. Again, the details don't really matter here. The point is that you can use Ray to seamlessly scale XGBoost, run it in a fault-tolerant way, run it in an elastic way, and use that in conjunction with other Ray libraries. If you want to do hyperparameter tuning, you can just import the Ray library for hyperparameter tuning, and it's quite simple. You define some training function, and then you can do tune.run, and that will, of course, take care of all the details for you, like scheduling across a cluster, starting and stopping experiments, visualizations, integrating with tools like weights and biases or MLflow, scheduling running on GPUs, things like that. Similarly, so if you want to scale hyperparameter tuning, or training, there's just great libraries for that. If you want to do serving, you want to deploy your machine learning model, here's a code snippet showing how you can do it. You just import the Ray library for inference, for serving. You can define a class. Now this is not even using a machine learning model. This is just serving a Python class. It can be stateful. You can have state that's mutated between invocations, and then you can just deploy it. So it's very Pythonic and natural way to do serving. And the point here is, if you want to scale serving, whether that's machine learning serving or just serving Python functions, Ray has a great library for doing that. So one thing I want to mention is that, of course, you can use these libraries individually, and that's very powerful. But one thing that can be even better is if you're building applications that really need to do all of these things, need to do data processing, training, serving, etc. And one example is from Uber. So this is from an Uber blog post talking about model training. And really, everything is happening here on top of this Ray cluster, from the pre-processing, which is using Dask on Ray for data processing. It's using Horovod on Ray for deep learning, XGBoost on Ray for gradient boosted decision trees, RayTune for hyperparameter tuning. From the infra side of things, it's a lot simpler because there's a unified tech stack here. It's all running on the Ray cluster. And then from the developer side, from the user side, they're just writing a Python script and importing libraries, and kind of using them together, just like the way people use Python on your laptop. And they're not thinking about, learning how to use a bunch of different distributed systems or gluing them together or anything like that. One really quick example I want to give. This is, sort of another powerful use case of one of the Ray libraries. So McKinsey used reinforcement learning library on top of Ray to design this boat, which actually, in partnership with the New Zealand team, won the America's Cup, which is the top competition in sailing. So lastly, I just want to say, again, Ray is this framework for distributed computing, and there's this rich ecosystem of libraries on top. and you can run Ray anywhere. And if you're interested in getting involved in contributing or using Ray, I encourage you to try it out and talk with us on our Slack, community Slack, or our discourse forum. And I'll stop there. Thank you so much.
Thank you, Robert. That was very interesting. And we do have one question, and maybe if you have any further questions, please just save them for the general Q&A later. This is from Carlos Cordoba. What's the difference between Ray and Dask?
Great question. So I'll talk about the parts where they're similar and the parts where they're different. So one of the most, I think one of the biggest similarity is the task API, so the ability to decorate a Python function and execute that in a cluster. A lot of similarities there. I would say the actor API is perhaps the most heavily used part of Ray, which is about more stateful distributed computing and creating these microservices or stateful workers. And there's a difference in some of the libraries that we have. Right, Dask has a great data frame library, a great array computing library, and a lot of Ray's libraries are more focused on scaling machine learning, hyperparameter tuning, serving, things like that. That said, you can use them together. You can, and there are companies using Dask on top of Ray, and one of the benefits of that is you can use Dask libraries together with Ray libraries to build your applications.
Thank you. That was great. Yeah. Thank you, Robert. So I guess we'll see you later. And now we'll go ahead and bring up our next speaker. Henry Schreiner is the maintainer of PyBind 11, and we'll hear their update.
Okay, thank you. So it's really an honor to present on behalf of the entire fantastic maintainer team for PyBind 11. You can see us listed over here. And so today I'm going to talk very briefly about what PyBind 11 is, just in case you don't know, and then I'll cover what we've been doing. I'll cover what we plan to do, and then I'll look at a few related projects that we love. So PyBind 11 is a header-only pure C++, CPython, PyPy interface. There's really a lot to unpack in that sentence, but just to point out, it's just really easy to add this to a project. There's no special build requirements. You don't have to have the BJam build system, for example, or Boost installed, and there's no precompile phase, so you don't have to Cythonize or swig, run swig on some sort of file and then decide if you want to store the output file or not. It's just what you see is what you get. It's just written in C++, and it's not a new language. You don't have to learn how to think in Cython C, Cython C++, Cython Python, and C. You just have to think about in hopefully the language that the library you're binding in is C++, and then in Python. And it's designed just for binding. Cython was never really designed for binding. It just happened to be able to do it due to the way it was designed. PyBind 11 is a tool just for binding libraries. So here is a little example of usage. You just include the PyBind 11 header. And normally you have some other thing you want to bind, but we'll just define that here. And then you can create a module, and then on the module you just define the add, and the signature is inferred from what you pass in there. And you can add documentation, parameter names if you want. And then just to show you, this is actually a complete working example. You can do this compile line down here as of 2.7. It actually supports pipx. And you just run that line. You don't have to install anything, just have pipx on your system, G++. Pretty easy to change this to the Mac version if you prefer. And just run that. And it will actually compile something you can run. Then sort of also highlights that you don't need anything installed. The fact that this is the PyBind 11 was only temporarily put there by pipx just doesn't matter. You don't need anything to run. Your thing is extension is standalone. So here's an example of a little bit more that you can do with it. You can bind classes. You can bind as many constructors as you want. It supports overloading. You could define your set and get names exactly, or you could customize the view that you provide in Python. So for example, you can add a property and add the get name and set name as structures. And you can swap these out for lambdas pretty much anywhere. You can define the special method yourself. There's also some nice utilities to quickly to turn C++ operators into special methods as well, as you see. So there's really a lot of different features. I'm not going to go over all of them, but one of the key things is that this is simple enough to be used for all sorts of different tiny little projects. You saw you could fit the simplest possible project in a single slide really easily. There's almost 500,000 mentions of PyBind 11 on GitHub if you look through the code search. And it's powerful enough to be used for huge projects. So SciPy uses it, PyTorch, dozens of Google projects are using it, with many more to come. And so we really have a wide range of users. And it really supports a lot of different things. You can quickly and instantly vectorize a method or a function. Lambdas work pretty much anywhere. And you have complete control of what you present. Okay. So the original maintainer team, so Wenzel Jacob is the original author. We had a team of maintainers. Many of them have gone off to do other things. So in the mid-2020s, or mid-2020, Wenzel Jacob pulled together a group of some of the most active contributors and created a new maintainer team, which you see here. And we've been working on this. 2.6 was our first release with the new team. And then there have been a few changes this year. Aaron has joined. Boris has temporarily stepped away, hopefully temporarily. And Wenzel is now considers himself a regular maintainer rather than the lead. So in 2.6, we added a new CI system. This was a massive rewrite of the CI completely in GitHub Actions. We have over 60 jobs. You can see them over on the right-hand side of the screen there, just to get a feel for how many there are. We cover all the versions of Python that we support, different operating systems. We check our PyPy deployments. We have lots of tests for different compilers, and we even have a bunch of newly supported compilers. So we support the Intel and the NVIDIA compilers, both sets of them that they have, and test in just a really huge variety of different situations. We've actually discovered and fixed a bug in CPython 3.9.0. Please use 3.9.1 or better if you can. And we've also, I think we've discovered another bug that we're working on now. And we've also been discovering bugs in these, like the Intel and NVIDIA compilers, and we're working with the compiler teams on getting those bugs fixed. It turns out we're a really great stress test for a compiler. Okay. And then we've also done quite a bit of work on build systems for 2.6. We've really restructured the entire CMake system. We've integrated now with the standard CMake features. If you are using CMake, and if you want to use, especially if you want to use the new Find Python support, which we now optionally support, if you want to use that instead of the old Find Python libs, Find Python interp, we actually support that, and we help them fix, again, bugs in it. So we really recommend 3.18.2 or better, because those have bugs that we reported fixed. Again, we're stress testing the Find Python, and we support CUDA as a language, and several other things. One of the most important things is we also now generate fully portable config files. They don't depend on the compiler you're using or the operating system you're using. That allows them to ship them inside the PyPI package. So you can actually pip install it, and you can use CMake on the pip installed PyBind 11 package because it's fully portable. And we've also added some helpers for setup tools. We had one of the most popular examples for how to use C++ in setup tools or distutils, but now we actually have our own little helper there. The build extent build ext is completely optional. You don't have to customize the command. So if you're in a larger system and you already have customized it, that's fine. Currently, the only thing it gives you is the ability to automatically pick a C++ standard instead of choosing one yourself. So that's quite useful as well. And it also has some extra utilities. So if you are using setup tools for your package, we help out with that. There have been a variety of other features. One of the main focuses for the development has really been on stability and reliability. And but we have put a few features in as well. So one of the key ones here is, pun not really intended, is the keyword only and positional only arguments. So you can support Python 3 keyword only or Python 3.8 position only. And it actually, since we're writing it in the SciPy, it's supported from all different versions of Python. And several other different features here. More correctness checking, so common mistakes are caught sooner and you're warned much sooner. I have a post that covers some of these in more detail. And then in 2.7, again, the same focus on stability and reliability, but there's still a few nice features. Heavily ones that are focused on sort of the latest C++ and Python changes. So there's now an optional caster for the C++ 17 file system in Matplotlib, as long as you're using Python 3.6. And a variety of other smaller features. And we also now are using Nox, which makes it easier for new developers to contribute, hopefully. And there really has been another nice collection of fixes and edge cases, and we're still expanding the various checks. One of the big things that's happening is this Klein tidy cleanup. Aaron, the new developer, has been sort of wizard at the Klein tidy, and he's been adding a tremendous amount of Klein tidy checks and already been catching some performance issues and readability and modernization. So it's been really, really nice. And I'm happy to announce that PyBind 2.7 is available today. It was released a couple of hours ago. It also includes pipx support, which you saw earlier. So just looking ahead at what we're planning to do. So we have some refactors in mind. One of the big things that's been happening is the smart holder branch, which Ralph at Google's been working on. And this adds full interoperability with unique pointer, as well as shared pointer. It's an opt-in, and hopefully this will get merged relatively soon since we have now released 2.7. At some point, we will be dropping 2.7 and 3.5 support, and at the latest, January 1st, 2022. So I'm really happy to be able to announce that. And we also are planning at some point to work on optional precompilation, which really dramatically speed up compiles. And it just unfortunately touches everything in the code base, so it pretty much invalidates every PR out there. So it's been a challenge just to pick a time to do it. But we've seen at least a 50% improvement in compile performance if you ask for the opt-in. And we have a few other ideas. There is a roadmap that you can look at and see what we're planning. Pull requests aimed toward the roadmap will go in faster than ones that are not. So there's some other projects as well. PyBind 11 is actually a group of different projects. There are 2 and now 3 examples that are some of the most popular examples. If you do a code search, you'll see a tremendous number of people copy our CMake example. And those have been heavily refactored, rebuilt, and now support Conda. They now support CRBuild workflows. Apple Silicon's been added, and a bunch of other things. And there are now template repositories making it easier for you to generate one. And if you like to set up a package really quickly, there's also a scikit-hep cookie package that is based on the scikit-hep developer guidelines. It's not HEP specific, high energy physics specific. So it's one of the quickest way to just quickly produce a package, and then all the decisions are carefully outlined, and it has all sorts of correctness checking and stuff. And then there's a variety of other different packages, like a documentation parser and some things for the Bazel build system, etc. And outside of this, another project that we love, the heart is not showing up. CI build wheel is really important to us. It's a way to get binary distribution. We actually share 2 maintainers with CI build wheel. It's not really a surprise. And this supports all different CI providers. It was recently added to the Python Packaging Authority. And we are in close collaboration with Mini Linux and shared maintainer, in fact, and PyPy devs. And this is a tool used by Matplotlib, MyPy, scikit-learn, and a bunch of others. And 2.0 was released today. Major new addition, it drops Python 2 and 3.5 support, which allowed us to unpin all sorts of different things that were stuck. Audit Wheel 4, for example, the latest PyPy. So if you're using PyPy, this is recommended. Audit Wheel 4 will give you slightly different wheel names. lots of great things there. And it has the pyproject.toml support. So you can now put your configuration in your pyproject.toml file. The sort of goal of CI build wheel always has been to separate you from your CI so that you wouldn't be dependent on your CI. And this goes even further with being able to just specify everything that you need inside your pyproject.toml. Makes it really easy to run locally if you're building Linux or cross-compiling Linux or emulating, Linux or using Windows. Mac OS, we still don't recommend running it locally because it installs things globally. Okay, and it also adds Python 3.10 as a pre-release, which you can opt into. Okay, and then another one that we love, which has a long history here at SciPy, is scikit build. Our CMake example is actually, as I said, one of the most popular examples, but this really duplicates code for everyone. For example, we added Apple Silicon support. Now every person who's copied our example has to add it. We now have a scikit build example that was new in 2.6. And scikit build itself is just the CMake setup tools adapter from Kitware, introduced at SciPy in 2014, renamed to scikit build in 2016. I think also at SciPy, and includes CMake for Python and Ninja for Python. And so two maintainers, one from Pybind 11, one from CI build wheel, have joined the scikit build project. So some of the initial things that you see from that are the new same-day releases for the CMake 3.21, Apple Silicon support, powered by Knox, powered by CI build wheel, of course, and the Ninja for Python as well. And with the scikit build 0.12 was not able to quite make it out today, but hopefully will be out soon. I get very grumpy when I have to debug Microsoft Visual C stuff. It usually requires I boot up a Windows machine, which ruins my day. And then, so that should be out soon. And that includes Apple Silicon support. And we have a really fantastic plan. Some of the more ambitious things will probably depend on funding, but we have some great ideas there for scikit build. So I think you'll see a lot more in the future coming in. So, and I would like to thank the various things that have made all of this work possible. Thank you.
Thank you, Harry. Congrats on the new release, and may everything go well. And I will love to hear more later about the new maintainers team that you just onboarded. So I'm very interested in hearing about that. I believe we do have time for one question, and we have one here, which is from Thomas Caswell. If you have existing C++ extensions, is it worth moving to Python 11?
I would think so. So I think it's certainly, if you're using Python, which wasn't really built to do this at all, it's been a huge thing. We've been moving, and in scikit-hep, we've been moving some of our things to Python 11, like iMinui, the fitting tool that's used in astronomy and physics. And it dramatically reduces the maintenance burden of keeping those up. Now, it does depend a little bit on what you're doing, but in most cases, Python 11 is very easy to maintain and keep up. It's very natural. So usually I would say yes, but it does depend on what you're doing.
Yeah, like many things, the answer is it depends, right? Thank you for that. Thank you for the presentation. That was wonderful. And our next presenter was Max Klein, but I believe he's not here. So we will go to the next. Oh, he is. Wonderful.
Hi.
So, hi. Next up, we have Max Klein, core developer of JupyterLab, and he's going to tell us more about making JupyterLab more accessible. Accessibility is a subject that is very close to my heart, so I will love hearing about that.
Well, you might not. It's been a bit frustrating, but I'll tell you guys all about it. Okay. Hi, everyone. My name is Max Klein. I'm a core contributor to JupyterLab. I think my name is listed wrong in the schedule for some reason, so they used my GitHub name. So the thing that I'm going to talk about today is the ongoing effort to make JupyterLab accessible. Let's see. So for those who are unfamiliar, what JupyterLab is a next generation editor for interactive notebooks. So relatively simple example where you have like you're editing a notebook, and then you also have a file browser in the same window. And JupyterLab can also do much more complicated things where, for example, you have multiple different notebooks written in different languages, all open, in the same window, as well as, some advanced visualization stuff, and then other tools, such as the metadata editor that's shown on the left there. And before I dive too deep into the issues with JupyterLab and accessibility, first I want to talk about what accessibility is. So according to W3C, the web standards people, accessibility means that websites, tools, and technologies are designed and developed so that people with disabilities can use them. More specifically, people can perceive, understand, navigate, and interact with the web and contribute to the web. And so the problem is currently that's not really true for JupyterLab. So in formal terms, the issue is that JupyterLab's UI is not compliant with the WCAG 2.1 standard. WCAG is just a standard that's put out by W3C for accessibility compliant websites and web apps. And so kind of the question, or the interesting thing, is that all modern browsers include a complete accessibility framework. So kind of the question is, why is a browser-based app like JupyterLab just not accessible by default? Why doesn't it kind of just work? And the basic answer to that is that interactive web apps with complex custom UI components will tend to almost always break the assumptions that these built-in accessibility frameworks make. One big example that turns out to pop up all over the place is the fact that in JupyterLab, the button elements that we display to people for all kinds of interactions aren't actually button elements, but they're instead divs with custom mouse handling. And because of that, essentially the accessibility frameworks don't really know what to do with them. So they're kind of handled poorly. And so for the past 8 or so months, I've been helping to spearhead a accessibility working group for Jupyter and JupyterLab. And kind of our initial goals, we're trying for, rather than to necessarily fulfill the complete WCAG standards to start with, we're just trying to, as a beginning thing, for people with physical or motor disabilities who want to be able to make the app so that it can be used and navigated using only a keyboard. And then for people with visual issues, just on the really simple level, we're trying to make it so that the layout is more helpful for people with issues, just by making sure that everything follows the basic sizing and color contrast guidelines. And then more complicatedly, we're trying to make sure that everything in JupyterLab is compatible with screen readers. So screen readers are essentially like for people with serious visual issues, they're able to help them navigate various websites and web apps and kind of like translate them into some kind of spoken narrative. And so most of our progress has been kind of at the very, very low level in terms of like essentially poking the right holes in our low-level UI framework. So there isn't that much to show off yet. There are a couple of things. For example, this what's called a skip link. So a skip link is basically just a way when somebody initially navigates to the web app that they're able to easily, just using a keyboard, skip to like the important parts of the app. So I'll demonstrate what we've got for that. One second. So can everyone see my screen? Not entirely sure. Okay, cool. So basic skip link works like this. So you're in the URL bar, you hit tab, and the first thing it will go to is this pop-up element right here, which by hitting enter, it will then navigate over to the file browser there. You can then filter your files however you want. And so this is obviously still very incomplete, but the idea is that we're going to work on expanding it and making it accessible to our extension system so that third-party authors who contribute extensions to the ecosystem can also build in these accessibility features. Back to where we were. Another thing that I've been putting a lot of time into lately is making an accessible version of a tree grid widget that can be reused in various places in the JupyterLab UI. So this turns out to be fairly involved. So what a tree grid is, basically I'll show you. Okay. So for example, I've been working on this thing, like this external project called Tree Finder, which is this implementation of a tree grid that includes these accessibility features. And so it's basically just, like in simplest terms, a grid, some kind of table that is also a tree. So like certain nodes can be expanded and or collapsed. And so the way this has to be handled in terms of WCAG and accessibility is they're actually like very specific HTML attributes that have to be added to certain elements within the widget. For example, RA expanded is something that's just for this kind of tree widget, where it's essentially just helping to annotate whether like a particular node is expanded or not expanded. And so currently I have a prototype of that that's functioning as the file browser for JupyterLab. And so as I go through the implementation of it, I'm also adding in these accessibility features. And sort of the tricky part for this, for example, is that this is actually a virtualized table. So the only rows that actually exist are the ones that are being displayed. So this creates some interesting kind of corner cases for the WCAG standards and ARIA labeling in general. It's kind of an ongoing research project to figure out the best way to handle this. Okay, and so in terms of what we've learned so far over these last months, that I can kind of share with other groups and other maintainers, it's mostly like I said, a lot of the work has been sort of frustratingly slow, and so mostly what we've learned are pretty simple things, but we were kind of chasing our tails for a while before we figured this stuff out. So kind of the simplest thing, without even getting into the WCAG standards or like the best way to deal with all this stuff, kind of the simplest guideline is stick to vanilla HTML where possible. So that example that I gave earlier about using buttons instead of custom or divs with custom behavior. Like there's many cases where people will create very complicated custom components, either won't bake accessibility in terms of like ARIA labeling and all the other required things, or in some cases it just won't work right unless you actually use the kind of intended HTML elements. Another thing, this was kind of, I guess in a way surprising to me as a code developer, is that we really did need outside expert help in order to figure out kind of like how to both how to get started on this work and then kind of how to plan it out, figure out what was actually like most important. And so we needed help both from subject matter experts who have experience implementing WCAG compliant UI, and then also just people from the community of folks with disabilities, because you're not really going to be able to tell whether something's actually helpful unless you get that kind of feedback. And then kind of the last thing, we found over these last months that essentially, all of us are putting in some part of our time on working on this accessibility project, and it's really not enough. So we need just given the scope of JupyterLab and given the scope of what's going to be needed to make it fully accessible, we really do need some full-time staff, whose primary focus is this accessibility work. So after a lengthy search for who would actually give us a grant for this kind of work, we currently have an in-progress grant application at the Chan Zuckerberg Foundation. And if it goes through, we'll hopefully have enough funding for at least 2 full-time people working on this. And we're hoping to hear back later this month. And you can follow along with our accessibility progress in the grants if you want at this GitHub repo. We post all our weekly meeting notes and also just various information there. And I'd like to thank all of the other people who participated in the accessibility working group. Isabella has been great just organizing everything, and Thomas, last name left out, I think for some work conflict reasons, has been he's our resident subject matter expert. He's just been incredible. Yeah, we kind of initially couldn't figure out our accessibility. I don't know. I kind of want to use a crude epithet here, but essentially he helped us figure out where to get started and where to go from there. And then everyone else who's been a part of the working group, everyone's been great. And yeah, so I glossed over basically everything because it's a short presentation. So if anyone has any questions, I'd be glad to answer them.
Thank you, Max. That was really cool. And I've been following this work closely because, just super interested in accessibility. And this is something that definitely would benefit a lot of our communities if we work together on it and brought some common solutions. So we do have a couple questions that I think we have time to. So first, are there tools that scan for and report common accessibility anti-patterns, like the div with mouse event handling example you mentioned? If not, would such tools be useful to build?
Sorry, can you repeat the question? Oh, tools that scan, is it the,
yes,
are the tools that scan for and report common? So there are certainly lots of auditing tools. I guess the issue is that there isn't really something that's meant for there's plenty of stuff that's meant for complex websites. There isn't really much that's meant for complex web apps. So JupyterLab is in some sense just and kind of independent application that just happens to be running in a browser. And given that level of complexity, I think just the automated tools fall short at the moment.
Do you think that's something that would be useful to build, or would it be better to?
So
we know that for accessibility, it's also useful to have actual humans testing for accessibility.
I mean, I think that's critical, but at the same time, how to put it, we have enormous gratitude for all the folks who have helped us out so far, who've come by and told us their stories and kind of their struggle. And some of it just really sucks, and I wish I could do more, yeah, no, it's kind of heartbreaking to hear some people talk about how they got interested in data science, wanted to get into it, and then sort of ran into a brick wall when they actually tried to boot up Jupyter and use it. It's the exact opposite of what we want to have happen, and so we're working to fix that.
Yeah, I think that sounds great. And fingers crossed for that grant. Let's hope
I
you
hope
get
so.
it. Thank you so much. So we do have another question, but I think I'll leave that one for the general Q&A or maybe the panel later. So because it's a larger question about what can the community do to help scale up the impact and availability of the accessibility experts. And I think that's something that is for a lot of projects. So maybe we can discuss that later, if that's all right.
Yeah, we have to kind of like generalize some of this knowledge as we gather it.
Exactly. Okay, so thank you so much, Max. And we'll go to our next speaker now, who is Hannah Eisenman from Matplotlib. Hannah is here to tell us what's new in Matplotlib and how you can get involved in the project. And I can't wait to hear about that. Welcome, Hannah.
Hi, y'all. My name's Hannah. I'm a graduate student in computer science, and I'm Matplotlib community lead. And this talk is actually going to be more about how, as a grad student, my dissertation is a proposed re-architecture of Matplotlib. And apparently my screen is not sharing. Is it? Is anybody?
Yeah, it's totally sharing.
Okay.
You're good.
Okay, thank you. So I'm here to tell you about kind of my dissertation research in some ways. And so first I want to say thanks to sorry, my slide deck has lost its mind. I want to say thank you to the Chan Zuckerberg Initiative for funding the work on 2 rounds of the EOS. They're funding me, and my collaborators, Thomas Caswell, who is the project lead, and Mike Bothberg, who is my advisor. I also want to thank Sam and Melissa for chairing this session. YT makes the best visualization slides if you kind of want to see more of this kind of work. And the Matplotlib team has been absolutely amazing in just me trying to get this work and be supportive and everything. So what are we doing? Like, why does Matplotlib need a re-architecture? Well, what we're trying to do is Matplotlib has all of this long-standing 20-year-old API, right? It's really organic. It's gotten like really deeply nested and entangled in places. And so the goal here is we're trying to kind of disentangle all of that. And the way we're going to do it is we're going to try to identify like what are the stages of visualization. We want to formalize this in a mathematically rigorous way. And then once we have these formalisms, build out a new API that implements these formal concepts. So what is Matplotlib's job? It is a visualization library. And the job of a low-level visualization library, sorry, I'm sure going too fast. The job of a lower-level visualization library is to regulate the transformations from data space to visual encodings to graphic. And so what this means is like if I have a NumPy array, I choose color maps for it. So that's how I decide which number maps to which color. And then I assemble that into a heat map. Or if I have a line data, I decide what is the X, what is the Y, and I assemble that into a line plot. And so Matplotlib will provide you the components to do that, and will also provide you with the components to go from the screen space back to the data so that we can do things like panning and zooming and interactions. And how does Matplotlib do this? Well, that is the artist. And the thing is, the artist, which is the object in Matplotlib that basically is taking your code and your input and painting it to the screen. And the thing with the artist in Matplotlib is it mixes up all of these stages. And how do you know it mixes up all these stages? Well, have you ever tried to update a line plot or a scatter plot? In Matplotlib, the line plot gets updated with a set X data, Y instead of Y data. And the scatter plot gets updated with a set offsets. And if you ever look at an array, it gets updated with a set array. And the reason all of these methods are different is because the line plot, the scatter plot, the image have different concepts of what data looks like. And that'll again propagate back into how you interact with this. It propagates into how we apply the different visual transformations. This is why like units will work for some of our plot types and not others. And so what we're trying to do here is, if we can, by separating out these components, we can start regularizing the interactions between these stages, so that instead of it all being baked into like, what is this notion of a plot, it's more, these are our notions of what color conversion looks like, and these are our notions of what assembling into visual graphics looks like. And so, yeah, in Matplotlib, this is why this is our artist, which is like, for example, the scatter plot is a path collection object that takes in a path object, and will go out to a scalar mappable object, and will turn a collection object. And if you've ever tried to if you've ever tried to read the Matplotlib source code, it's basically UML soup when trying to think through the paths. So again, our post-V architecture is, we have data, it is independent. We have the maps from data to visual encodings, and then we have separate functional maps into the graphic, and then we have a separate functional map back. And the other advantage of this is, if we can disentangle all of these maps from each other, then we can push more ownership of these to you, the maintainers of different projects, which means, for example, a data container library like Pandas or Dask can help own the map from graphic back to screen. So what are the rules? Like, what are these maps? How do you compose components, right? Like, because I just said Dask, we want to make it so Dask can own the component. Well, if they're going to own it, we have to give them the rules to own it. And so a lot of this research work has been, what are the rules of these maps? How do they have to be implemented so that the thing you get back is a valid visualization? It is a valid graphic. And so the first thing we have to think about is the map from the graphic back to the data. And we want to do this, we want to conceptualize this map in a data independent way, right? Like I was saying, Matplotlib, currently the line plot thinks it is its data is a 1D continuous space. The heat map thinks its data is a 2D image. So we want to not have that happen, because that is how we end up having to tie the data model to the graphic. So we start with the data, it's the graphic, here a scatter plot, and this scatter plot is fed by data. It is fed by 3 dots. Each of these scatter plots has a map back to the data. The first scatter plot is JFK, the second is Hilo in Hawaii, the third is Barrow in Alaska. They're all independent of each other. And because they're independent, they're discrete, which means that, and we are just mapping these scatters, it is the temperature and the precip of this data. Because it is discrete, if I shuffle the data, I haven't lost anything because my mapping is independent. And what we're talking about when we're thinking about this topology, right, is, again, instead of thinking the scatter, it is backed by this specific type of data structure where, like, the scatter plot has maps back into this data, which, like, let's connect it, right? Let's connect the scatter. And so now we have a line through all of these. And so each of the corners here have a map back into the data. But if I have a middle, what about that middle of that line there? I have no map back. I have not satisfied the topological constraint here that for every piece of the graphic, I have a point back in the data. And therefore, I've written an invalid component that goes from the graphic to the data. And so we're trying to say, you can't do that. But if you do write these components that are topologically sound, then we don't really care what data type you're using underneath the hood. You just have to have it so that the continuity of the data respects the continuity expected by the graphic. The next thing that we care about, right, and so that's from the graphic back to the data, but we're visualized with the library. We need to get stuff on screen. And so the getting stuff on screen is the data to graphic pipeline. And the thing that's important there is equivariance. And equivariance is about preserving structure, respecting the properties of the data. So, so the thing is, right, if I have the precipitation and I am plotting it, What I want to do is I want to take the y-axis here. The y-axis is the precipitation data. This is for JFK. It's one station, so it's a time series, so it has that 1D continuity. And what we're trying to, and so this data is ratio. It starts at 0. It is a float. And so what we're saying is, what we need to do is, in the data, the distance between January 1st and January 2nd is the same, is proportional to the distance between January 2nd and January 3rd. So in the graphic, those proportions stay the same. And so if we scale the data, so we convert our millimeter precipitation to centimeter precipitation, in the graphic, that relative distance better remain the same, because that's what it means to faithfully preserve the visualization. And so, okay, why, right? Like, what does this give us? Why is Matplotlib going through all of this pain? So in particular, it is because nowadays modern data problems are, they're multivariate, they're multidimensional, they have multiple continuities, and they're just very complex. So take this example. We have a scatter plot of our data, plus we have the line plot of the time series, plus we have the time series of this precipitation. And these are all linked. So for example, right, the green is all Hawaii. It is the precipitation of Hawaii, it is the temperature, and is the legend, right? All of these elements of the graph map back to the data point. So what does that mean? What that means is, right, if I want to zoom in on July, I want to zoom in on the precipitation, I want to zoom in on the temperature, I want to zoom in on that scatter, and I all need to zoom into the same region. And so if we have this concept of like if we encode this, instead of trying to encode this as a scatter plot and line plot and a secondary line plot, this is one data structure that has this 1D continuous topology, and underneath has this 1D scatter, then it is all connected. And so all of these plots are hooked together topologically, so that if we have a subset on the topology, it propagates back to all the graphics. These also are all encoded in the same way visually, right? Here, Alaska is all in gray. So if I change the color of Alaska in one place, I need it, like in the legend, I want Alaska, that color, to change in both line plots in the scatter. And so if we have this functional model and this notion of like, this is the function that does these conversions, and you can just drop it in, then we can think about doing this. It's a consistent update that propagates through every artist in this figure, rather than having to individually set this new object in every one of these images every time we change a color. And the way this gets really powerful, right, is that we have 3 points here and we have all of these arrows back. And this is just for one date here, right? We really have all of these dates. So think about all those arrows. And so what we're saying is we can update all of these arrows in a very consistent manner. And so what this gives us is, if we decouple the data, the visual encoding, and the plot, we can provide easier, more reliable, more consistent code that is easier to maintain. And we can have this generalized data model, so we stop thinking of everything as an array. And if you want to learn more, the conceptual prototype is at my GitHub, which is my dissertation research. And if you want to talk more about it, you can talk to me online, by email, on the Gitter, on the discourse, which I wrote here to discuss. Thank you.
Wow, thank you, Hannah. That was so enlightening and super cool to see how things go behind the scenes. I have to say that I didn't know any of that, so that was amazing. Do we have any questions? I don't see any in the Q&A tab, but if you have any.
Yeah,
If
so
not,
the topological constraints, it just means really that a line plot is backed by 1D data and a heat map is backed by 2D kind of things. Sorry about that.
will this help? So we have a question by Max Klein. Will this help with geometry issues like the type fit stuff?
Oh, the layout managers. we do plan to propagate it all the way up to like things about artists. Right now we're focusing like, because those are also artists, so they're also going to be part of this. So the answer is maybe, but we haven't like worked through what that looks like in a conceptual prototype yet.
Very, very cool. And I see that some people have shared those links in the chat as well. So if you want to check out the slides, Hannah's dissertation, they're all in the chat. Thank you so much. So maybe we can have some more discussions about that in the panel later.
Yeah.
Thank you, Hannah. Okay, so next we have Carlos Cordoba from the Spider IDE. And he's going to tell us about the new core new features added to Spider this past year. And I have been following this closely, so I'll be glad to see the stuff that Carlos has to present. Welcome, Carlos.
Hi, everyone. Can you hear me? Okay, thanks. I'm trying to share my screen, but I don't know if it's already there or not.
Yes, we can see your screen now.
It is. Are you seeing my presentation or the?
We see both.
Are you seeing both? Sorry about that. I don't know how to change
Hey, Carlos.
to just one screen.
What you can do is you can start presenting the Google slide, and then when you're selecting what tab you want to share, it'll show up as an option.
Okay. So, is it okay now? Oh, okay.
No,
Sorry.
you still.
So yeah, so stop presenting for now, and then reselect
Sorry.
the tab with the presentation.
Mm-hmm. Let me try again.
But you do have to start the presentation first.
Okay. Let me see what is the one that I need to do. What is this one? Nope.
So meanwhile, let me just remind the audience, if you do have questions and you want to leave them at the Q&A tab, we can copy those for later for the panel presentation, so they won't be lost.
Okay. Is it okay now?
Yes, now it's perfect. We can see your presentation.
Great. Thank you. Okay, so as Melissa said, my name is Carlos Cordova, and I'm going to tell you today a year in Spider development. So what we have been doing the last past year. So first, well, a little bit about me. So I have been the Spider maintainer since 2013. Right now, I'm the Spider manager at Quantsite. So I'm leading a team of about 10 developers between contributors and people part of Quantsite that are maintaining Spider. I'm really passionate.
Sorry, can I just interrupt you for a minute? Someone just mentioned in the chat, can you show this in presentation mode? Is that possible?
Sure, yeah.
So that we can see better.
Okay. No. Sorry about that. Well, is it better now?
I believe so, yes.
Okay, thanks. Okay, so going back again, well, I work at Quantsite as a Spider manager. I lead a team of about 10 developers that maintain the project. I'm really passionate about Python since 2016. I am a physicist by training. And for those who don't know, Spider is an IDE for scientific computing, specifically focused on scientific Python. And it's also created with Python. So it's a really nice project about that. And it's also maintained by most of the people that participate in the community are also scientists and engineers, so that data scientists. So we're also interested in having something that works for us. So in the past year, one of the main things that we did is to renew our interface. So on the top of this screenshot, you can see how Spider looked in Spider inner version 4, and below it's version 5, which was released last April. So there are very important things, like for example, you can see here in the main toolbar, the icons were very jammed, very scrammed together, and there was not so much room for breathing. So we decided to change that in Spider 5 and make the interface to look much leaner and easier to the eye. We also changed the colors of the palette that Spider uses and try to match them and make them work together, because some colors, like for example these ones in the Rail Explorer, were not well picked up to work with the rest of the colors, and now they look very nicely. And this was work that took us like 6 or 8 months. It looks kind of not so hard, but it was really trying to decide all of these things. Another important thing is that we were using before several icons from different icon sets, like for example, Phonos and Material Design, and that look make the interface a bit out of place. And now we decided to unify and use all icons from Material Design, and we also design some specific icons, for example, to that, like these ones, to run cells or run selections that are not part of Material Design, but in this case, we make them follow like the design patterns of the icon set, so that things look much better now. And lastly, for example, we added more space also in the tab area, like in this part of the editor. Again, things look much more nicely and together. And we also did this not only for visual reasons, but also for accessibility reasons. So for example, if buttons are very small, or the contrast between different states in buttons is not good enough, then people that is visually impaired can actually click them. So it's not only for aesthetic reasons, but also for accessibility reasons, and we invested a lot of time in that. And besides that, or thanks to that, we also created a new light theme. So not all people likes to see things in dark mode, although that's the fashion these days. But the huge refactoring that we did behind the scenes to support better accessibility and a better color system allowed us to create this very nice light theme, which is also, well, it has at the moment some small accessibility issues, like for example, the color in the green and the background is not so easily to distinguish, but we plan to fix that in the future release. But besides that, we think it looks really nice, and it's also a really great improvement that happened in Spider 5. In the last year, we also performed our first community survey. So one of the things that we identified through that community survey is precisely that our interface was not looking great, and people had many complaints about that. But also, we gathered information about how people use Spider, like in this slide that I'm showing, and what are the features that they like the most, what are the things that they are struggling to get correctly, or to make them work correctly, or what are the improvements that we would like to see. And part of that part of the fixes for that went to Spider 5, and others are planned for future releases. But throughout this, I want to let you know that we are here in the community, and we're trying to fix things or to improve things for the community, because really you are the ones that use Spider, and we want to provide you with an environment that really fits your needs. And one of the things that we discovered thanks to this community survey is that people struggles a lot when they are installing Spider, or especially when they're updating Spider. And to try to solve that painful process, what we did is to create installers for Windows and Mac. And as you can see in these screenshots, those installers are very simple, are really like click and go installers. And they provide a Spider and also our main optional dependencies like Matplotlib, NumPy, Pandas. So as soon as you install Spider throughout these installers, then you can start using it without worrying about anything else. Of course, the only main issue that they have is they don't include all Python libraries that you would like to use. And for that, I'm going to show you later how to deal with that. But at least you have a very nice, a very simple environment that you can install very easily. And that will allow you to improve, to not suffer when you want to install a Spider or you want to update it. Besides that, in the last year, we also improved our debugger and made it really interactive. So in Spider 4, for those who use it, our debugger was not that great until our 5.2 version, which was released last November. But now you can do everything in our debugger. You can do everything you can in IPython itself. And what do I mean by that? That you can make plots in our debugger, both inline and interactive, as you can see here at the bottom. You can have code completion, and you can have also syntax highlighting in the debugger, and you can write multi-line statements as it's shown here. And you can also run IPython magics like timeit, for example. And finally, our debugger is connected to one of the most important things in Spider, which is the variable explorer. So basically, our debugger is now like an IPython session that allows you to explore things when you are in a specific frame in your code. And that's something that, I mean, it took me years to understand how to, I mean, what was the thing that scientists really want from the debugger? And I think this is it. I mean, we work really hard to provide this. And I think everyone, or I hope everyone will enjoy working with the debugger like this, because basically it allows you to explore your data or to make plots or to change variables in every specific point in your code, not at the end or not after the code has run. We also added in 4.2 a detection of conda environments. So that's something that goes well with your installers. As I mentioned before, our installers don't come with all Python packages that you would like to use, like for example PyTorch or scikit-learn or other important packages in the ecosystem. So to solve that, we added this feature that if you install Anaconda or Miniconda in the default locations, then we will detect your environments and show them in our preferences, specifically in the Python interpreter entry. So you will be able to select the environment that you want, and after clicking apply and OK, your consoles will use that environment by default, and you could make the computations that you like with the packages in those environments. Another important thing, and this is something that we did in Spider 5, is to add a new API. So the thing is that we receive a lot of enhancement requests that, for example, please add this button or please add this feature. And sometimes it's too much for us. And sometimes it's too specialized that we don't think that it should belong to the core of Spider. So to solve that problem, we wanted to make Spider yours by allowing you, the community, to create your own plugins. And this new API is powered by Qt, PyQt, and Python. So Qt is the graphical toolkit that we use in Spider, and it's a toolkit that has 20 years or more of existence. So it's very mature. It's used in a lot of applications or in a lot of environments. And PyQt are the Python environments for that. And behind all that is Python too. So you can program or extend Spider using Python, which is really nice. And on this graphic, that you can see how the interactions between different parts of Spider were working in Spider 4, and it was really, really messy. We tried to decouple that and make it much more simple to understand. So now you can add, for example, toolbars, menus, status bars, widgets, and layouts, custom layouts to Spider. You can also add code completion providers. So for example, if in the editor you want to have specialized completions for one thing or another, you can build your own plugin using our code completion providers API and make that work in the editor. We also have new registries to access actions, buttons, and toolbars and menus in Spider by identifiers. So if, for example, you want to add an action in a menu between two other actions, then it will be much easier now to do than in Spider 4. And finally, our API now is much more modular and decoupled. So hopefully you will also enjoy extending Spider through that. This is, of course, a work in progress. We haven't finished that yet, and we will still work on improve it throughout this year, but many of the things that I mentioned are already in place, and hopefully you will enjoy, as I say, working with this API. In the last year, we also had a huge impact on especially on YouTube, on our YouTube channel. So this slide is dedicated to show you that the media content impact that we have had. Or the name of our channel is Spider IDE on YouTube. Right now we have 1,600 subscribers, about 125,000 views, which is, I think, huge for, I mean, a small project like us. We have live streams or what we call affectionately Spidercasts every month or every 2 months with different topics. And we talk, for example, about the release of Spider 5 or the new debugger features that we showed you in more detail. We also have tutorials, and this week we also started a small section called FAQs. So for example, those are very short videos dedicated to specific topics. Those are connected also to the FAQ section in our documentation. And I also would like to take the opportunity to give you a small spoiler alert. And this is that we're going to deliver some live workshops to teach you how to use a Spider for a specific context. Those are going to happen in the next 3 weeks. And the announcement will happen on our Twitter account, which is Spider_IDE. And the workshops are going to be about financial data analysis, scientific computing and visualization, and plugin development with our new API. So please stay tuned for the announcements on our Twitter account. And another thing that is also a spoiler alert is that we are changing our branding image. So this is the current logo and splash screen for Spider, and this is still in Spider 5. So this is the icon, and this is the splash screen. And we have been using this image since the beginning of Spider, since Spider 1.0. And it was created by Pierre Revaux, who was the original author of Spider. And we have been thinking to change it for some time, but we haven't found a good designer to help us with that. But fortunately, we did that. And this is the new image of Spider. And this is our new icon. And this is the new splash screen. And hopefully you will like it. We involved the community and past contributors to help us decide our new logo among a couple of options. And this is going to be available since Spider 5.1 to be released at the end of the month. And to finish, I would like to thank the Spider team, because they are basically the ones that have made all these features that I showed you possible. And I would like especially to compliment Isabella Presero-Floyd, our designer, who has helped us to make the many improvements that I showed you at the beginning about the new light theme, the new dark theme, the accessibility improvements, etc. etc. She has been fundamental with that work, and I really appreciate her work. Sorry, a lot. But besides that, there is these 4 people in the bottom of these pictures. are a part of Quantsite. So Quantsite has been also really helpful to keep maintaining Spider, because this is now really a team job. I can do it by myself. And they have been working, for example, Juanita on the new docs and videos, Danielle on the Windows installer, Edgar on the new Edgar and Stephanie in the new API, and Ryan has helped us to create the Mac installer, and he's a volunteer. And so that's it for today. Thanks a lot for your time, and please don't forget to subscribe to our YouTube channel for more video content in the future. Stay tuned on Twitter for the announcement of our workshops. And if you want to have a very simple and hassle-free Spider experience, please use our Windows and Mac installers. Thanks a lot.
Thank you, Carlos, and huge congrats to the whole Spider team for this amazing effort going on in the past few months. I've been watching them closely as my colleagues at Quantsite, and it's been super wonderful seeing you build all that. And especially if you haven't checked out Spider's YouTube channel, please do. Juanita's videos are just awesome. And she's been doing a great job with community as well. So congrats. We do have one quick question, just because we're running a little over. So what tools did you use to write the Mac and Windows?
Yeah, so for the Windows installer, we use a tool called PyInsist, which is a very nice tool written by Thomas Kloiber, which is also part of the Python scientific community. We tried a lot of options, and for example, Conda and PyInstaller, Py2exe, but the best one for our use case was PyInsist, which is actually very simple to use because basically it installs everything in a Python installation, and then it grabs it up and put it in an MCC installer. That's it. And we build it using with GitHub Actions. That's for the Windows installer, and for the Mac installer, we use Py2app, which is very well known in the community, also very well maintained, and we also built the installer using Py2app with GitHub Actions.
Cool, thank you. And I hope we will get a chance to talk a little bit more about that in the panel discussion later. So if you want to know more, please stick around. Thank you, Carlos. Our next presentation is actually a pre-recorded talk. Our speakers, I think they are also here. So after we play the video presentation, you are welcome to ask questions. In this video, Colin Carroll and Predrag Grubsky will share their experience adopting typings with Arvis and GraphQL compiler.
Welcome to our talk about adopting static typing in large existing code bases. Static typing is very helpful, but if you're the maintainer of a large project that is currently not typed, you might feel that adding static typing might be too much work. I know I did. My name is Predrag, and I'm the author of Typing Copilot, a tool I built to solve this problem. I'm Colin Carroll. I'm a maintainer for Arvis, which is a visualization and diagnostic library for Bayesian inference. Arvis is about 40,000 lines of code. It's not as mature as Pandas or NumPy, what it is, but it is a very active library. It has a lot of contributors. It has a fair number of users. It's also an interesting library that it works tightly with a lot of other Bayesian libraries, but not all of them at once. And so we actually test against a number of Bayesian inference libraries like PyMC and Stan, but those are not direct requirements of the library. And this matters when we're thinking about type hinting and which libraries are using type hints. We're very conscious of the environment that we're working in. So the origin of this talk was when Predrag suggested adding typing to Arvis, and in a vacuum, as a maintainer, I would love my library to be really well typed, but I was really hesitant about the work that would go into adding typing and how much would this slow down development, and how much would this inconvenience sort of everyone involved. And so this talk is essentially about how he convinced me and what actually happened when we went and did it. He was not lying to me. He did have a way of adding typing to the library that was fairly painless and that I think is a good approach. Before we go much further, I want to talk about what
type hinting is. And so this is type hinting. We're just annotating functions, variables, returns with types. So here you can see that we're indicating that the square function should only take an int. And so this, as it stands, is essentially documentation. So it's telling the callers of the function that maybe you shouldn't be using floats or complex numbers. But until you use a tool like MyPy, it won't actually be enforced. So this is the general outline of the talk we're going to be giving. I want to start with what the difficulties are when you're adding type hinting to a existing code base, and these are the hesitations I had before adding typing to RVs. And I want to think about this from 3 different points of view. Essentially, these are the stakeholders in your project, especially an open source project, and sort of who you're thinking about as a maintainer when you're making changes. Let me introduce you to end user Emily. So of course she wants new features, but it might also be interesting to think about how she wants type hints exported to her code base. So in particular, she might be maintaining some internal code at a company or at a lab, or she might have her own open source library. And by RVs being strongly typed, it's going to help her library get typed. Secondly, contributors to the code base. These are often in scientific programming. These are often scientists themselves. So Kathy might be a grad student. She might be a researcher. And she might just be the only person or the inventor of some algorithm that we would love to have in RVs. So she doesn't care that much about typing. She cares about this algorithm, and we want to make it as easy as possible to get that algorithm into our library. I think it's so cool. There have been a few times where RVs and PyMC3 have had algorithms just a few weeks after they've been on the archive. So we don't want the pull request to take long, but we also don't want her to need too much hand-holding or too much back and forth in order to figure out how to add these type hints. Finally, maintainers, which is sort of all of us, we want to be able to merge with confidence. So once CI passes, we want that to tell us, hey, this is really good. As a maintainer, I really hesitate before saying, like, let's go and add type hints to 40,000 lines of code. That's a lot of code. That's going to be a lot of work. I don't want to do it. I don't want to ask someone else to do it. But if we're doing it a little bit at a time, we really need some way of enforcing some of that, but not all of the type hinting. And we don't want to fall backwards. So RV's had a contributor who for many years has contributed type hinted code. It's beautiful. He says it helps his own workflow, but since no one else was doing it, we weren't enforcing it with MyPy, it would get stale very quickly. Other people would edit those functions or call those functions with different types than he intended. And this feels bad. It feels like we're not respecting the contributors.
Adopting static typing in an existing codebase is tricky in 2 ways. First, since the codebase is inconsistently typed, maintainer Michelle has to set up many complex MyPy rules to make MyPy work. This is a large upfront time commitment, and maintainer Michelle might be understandably hesitant to do it. There are also significant ongoing costs. If CI is not configured to enforce the existence and correctness of type hints, then it's very likely that the type hints that do exist will degrade over time. Maintainer Michelle has to consistently update the MyPy configuration in order to avoid being in a 2 steps forward, 1 step back situation. And this is on top of ongoing work with contributor Kathy in order to ensure that new code contributions are also type hinted. Given these difficulties, it's not at all surprising that not many existing untyped projects are in the process of adopting static typing. Typing Copilot is designed to enable a workflow that addresses both of these points of friction. Typing Copilot finds the strictest possible MyPy configuration that does not produce any errors for your project. Under the hood, Typing Copilot runs MyPy with all checks enabled, then disables any checks that produced errors only for the files where the errors are produced. The remaining MyPy configuration is the strictest possible one for your project. No additional check can be enabled for any file without producing a MyPy error. In this way, Typing Copilot minimizes the amount of upfront work that maintainer Michelle has to do. Instead of manually creating a MyPy configuration for the project, Typing Copilot init will automatically create the strictest possible MyPy configuration that maintainer Michelle can use in the project's CI environment. And along the way, in a small number of cases, maintainer Michelle might need to resolve some type hint errors that MyPy does not allow to be disabled in its configuration. Typing Copilot then enables a powerful ratcheting workflow. Since the generated MyPy config is the tightest one possible, CI will automatically enforce the ongoing correctness and existence of type hints in your project. Since type hint quality can't degrade over time, it can only get better. And every pull request is an opportunity to tighten the ratchet further. Run Typing Copilot Tighten to generate a new, tighter MyPy configuration for your project if one is possible. Maintainer Michelle can even use the error if can tighten flag to ensure that CI catches any pull requests that forgot to tighten the ratchet.
So finally, we want to talk about 2 case studies on adopting Typing Copilot in open source projects. And the first of these projects is RVs. Again, when we first thought about adding typing to RVs, we went and just ran MyPy on it and found 361 errors. And so this was what sort of gave me a hesitation. We would have to fix all of these if we wanted to introduce MyPy into our CI. That would make us correct up to the default configuration. What we did instead was use Typing Copilot. Typing Copilot in it uses the laxest configuration possible. That still found 41 errors. That happened for the reason that I mentioned earlier. We had a contributor who was typing all of his code. Then later contributors and me were going and messing up all the typing that he had done, and we inadvertently introduced 41 errors. And these are pretty big, blatant errors, right? If the laxest configuration of MyPy still flags these, you're going to want to fix them. In fact, one of them was a user-facing bug, and we were able to find that without any users filing issues on it. Once we had fixed all these, so there was a small amount of initial work for fixing up Typing Copilot in it and adding it to CI. But now we have Typing Copilot Tighten into CI. This makes sure that every new contributor, every new contribution is at least as well typed as the codebase had been before. So this is exactly what we wanted initially, which was that we're always going to get at least as much coverage as we used to. The code standard is only going to get better. And now we also have MyPy running in CI, so that's going to guarantee correctness. So we get more coverage and at least as much correctness.
For our next case study, I'd like to tell you about adopting Typing Copilot in another project I maintain called GraphQL Compiler, which is about 100,000 lines of code. A few things stood out to me. First, any newly added code and new files has to be completely type hinted because Typing Copilot enforces the full set of MyPy rules against it. Second, if using existing untyped functions from those newly added files, those functions also had to have type hints added to them because of a MyPy rule called disallow untyped calls. This rule made sure that we had a strong positive nudge toward adding more type coverage over time, and that type coverage was actually quite easy to add because those functions were already top of mind and we had already figured out the appropriate types to use. Finally, every so often, Typing Copilot surprised us by tightening the ratchet on files we never anticipated. This was most often the case when adding type hints to an existing function that was widely used across the project. Every so often, Typing Copilot would find a file that only used that function, and that was the only untyped function that was used in that file. And as a result, having type hinted that function would be able to tighten the ratchet on that file, ensuring that it could never call untyped functions ever again. This is something that would be very difficult to do by hand, and Typing Copilot was able to tighten the ratchet for us in these situations for free. Type hinting tens of thousands of lines of Python is never going to be trivial. But at least for our use cases, adopting Typing Copilot made the process much, much easier. It's available on pip. You can get it by running pip install Typing Copilot, so give it a try. Thanks.
Thanks, Colin and Predrag. That was very interesting. And yes, I totally agree with the people who were talking in the chat about how wonderful those use cases were and the personas that you developed. That was really cool. Do people have questions? Let me just check the Q&A. Does anyone have specific questions for Colin and Predrag, or maybe you want to say?
Yeah, Predrag?
Sure. The reason I built Typing Copilot is because I think static typing is one of the things that, in theory, everyone would love to adopt, and in practice does find issues, but the startup cost was just so large. And so initially, I just built it for myself, and it's great to see that it's more useful than just for my own purposes. And if folks here use it, I would love to hear how it went. It's a one-person project so far, so I would appreciate any help I can get. But I would also love to just hear all of the positives and negatives that everyone ran into while using it. This is programming is a team sport, and I'm very happy to be part of a supportive community. And I would love to hear everyone's feedback, whether it's positive or negative.
And I would just add I sort of can't emphasize enough how little I care about typing and how much more I care about MCMC. And so having a tool like this sort of helps me as a maintainer to spend more time on sort of the science I care about rather than sort of the code quality stuff that I would rather someone else take care of. And so any tools for that are helpful. And, hopefully some of the other big projects around here have find some use from this, and I've loved all that they're sharing with us.
Yes, the fact that Colin agreed to A, adopt Typing Copilot, and then B, do this talk, I think is a strong positive sign that maybe this is actually a useful tool.
Yeah, thank you so much. And we know that those things can be heated discussions among developers. So thank you so much for taking that on. And if anyone in the audience has further questions, they can bring them up at the panel later. So please be sure to stick around. And thank you so much, Colin and Predrag. And we'll move on to our next speaker. We are running a little over. So Niels will have his time to present, but maybe we won't have that much time for a Q&A afterwards. So I'll repeat that. If you have any further questions, please bring them later to the panel session, and we can answer all those questions. So our final speaker for today is Niels Bantilan from Pandera, which is a statistical data validation library. And I'm really interested to know more about Pandera's roadmap and how the concept of statistical typing drives the API for Pandera. Thank you.
Thanks, Melissa. Hi, everyone. I'm happy to be back at SciPy again this year. Last year, I talked about Pandera, also kind of just introducing it to the community. But today, I'll be talking to you about the roadmap and moving towards better data testing tools for data science and machine learning. So I guess a little bit about myself. I'm a ML engineer at a company called Union AI, which builds ML ops tools. And so I'm one of the maintainers of FlightKit, which is open source package for ML orchestration. But I'm here today in my capacity as the author and maintainer of Pandera. And it started off as a data validation tool, but I think it's beginning to evolve as I myself and the community starting to form around it are proposing new ideas. And so let's dive into it. The outline of this talk is broken into 4 parts. So I'll first introduce data testing as a general concept, show you a Pandera quick start just for people who are not familiar with the project, give you a sense of the core value proposition and core API of Pandera. Then I'll dive into the roadmap, describing roadmap ideas and items through certain guiding principles that I've distilled based on conversations I've had with the community. And then finally, I'll give you some resources on how to contribute. So data testing is the colloquial term for schema validation or data validation. It's a fancy way of saying, are my data as I expect them to be? This is a quote from Eric Ma, one of, he is also a contributor, but also we've shared a few email conversations, and As an addendum to this blog post that he wrote, data testing can also be thought of as testing the transformation code that produces the data. So not only are we thinking about validating data itself, but also the functions that produce that data. And so this is, my life before Pandera. I do a lot of data cleaning, I do a lot of modeling. So, when pulling data from a raw source, maybe a flat file or something, I might have a data set that looks kind of like this, is just all in strings, and I need to clean it, get the types correct, make sure certain assumptions about the data are correct. So I might come up with this clean function here and do some cleaning. And now to test the clean function, I have a test suite, maybe in PyTest. And so now I have to handcraft some mock data to feed into the clean function, and I get some result. And now I might assert some exceptions that might need to be raised, but here I'm just asserting assumptions about the raw data, or the output of the clean function. And so I'm saying here there's a continuous column. It's some kind of number, and all the values are greater or equal to 0. And there's a categorical column, and all the values belong in the set ABC. Okay, so great. This is how I used to do things a lot, and it's still a valid approach, I would say. So the value that Pandera adds to this kind of concept of data validation or data testing is it provides this expressive and lightweight statistical toolkit for validating data frames. And data frames are kind of these specific tabular objects that are different from JSON. Data formats can potentially be reduced to data frames, and data frames can be denormalized or changed into other formats. But I worked with Pandas data frames a lot, so this is where my starting point was. So it lets you check the types and properties of data frames. It allows you to easily integrate with your existing data pipelines via function decorators. And it allows you, and this is a new feature since last year, to synthesize data from schema objects for property-based testing. For those unfamiliar with some of these terms, I'll kind of get into it further into the talk. So there are two flavors to Pandera. The classic, vanilla flavor, which the way I designed this was to make it feel and look like defining a Pandas data frame. So you have columns, and then you have this column object that encapsulates all the constraints that you want to express about this data frame type. Now, a collaborator who's done a lot of heavy lifting recently, just want to give a shout out to Jean-Francois Zinc, who basically opened up an issue and was like, hey, I kind of want this a Pydantic-like interface for Pandera. And so he basically built it out, and I was pretty hands-off and did some code review, but this is the chocolate flavor, I guess. And it looks very similar to Pydantic. You can define your columns via class attributes, and you can add types, type annotations, and further constraints via the field object. You might notice this coerce equals true keyword option. And what that lets you do is Pandera is evolving into to adopt Pydantic's approach of parsing as a primary thing that the library does, and then validation. So if you set coerce into true, Pandera is first going to coerce all the types of the columns before applying the validation rules to it. So this is really the core value of Pandera, where if I try to validate some raw data, it's going to coerce all the columns, the continuous one to the float. But then if certain validation rules are not met, like continuous containing certain negative values, it's going to throw an error. And by providing the lazy equals true argument to the validate method, it's going to try to collect all of the potential errors in the data frame before reporting back out to you. So this is really, the core interaction, core API for Pandera. It's parse, validate, and then this debug loop for helping data scientists, data engineers, machine learning people, anyone who uses Pandera or Pandas to refine their data structures. So I'll get into the roadmap. I'll highlight basically 4 guiding principles that are sort of the North Stars of this project. And these are really distilled from my own thoughts and also the community's feedback and ideas. And along the way, I'll highlight a few of Pandera's features and roadmap items for those interested in digging in and contributing. So the first principle is parse, then validate. So going off of the Pandera, the Pydantic documentation, both of these libraries guarantee the types and constraints of the output data, not the input data. So if I have some raw data, Pandera will first parse. In this case, the limitation is that it only does type coercion and then applies the validation rules to give you valid data out. So, sorry, what this means in Pandera is if we have our raw data again, it guarantees that input and output data frames fulfill the types and constraints as defined by type annotations. So I'll get into this by first defining the schema that I showed you earlier. And now if I want to summarize the data below, say I want to group by categorical and then compute the mean of the continuous column per category. Now you can see my summarized data function is super clean. By annotating my input clean data variable, input argument with the data frame schema annotation, and then adding the check types decorator to summarize data, what Pandera will do is first parse and validate this raw data that I'm feeding to it, and then pass in that valid data into summarized data. And so now all I have to worry about really is the actual summarization or the analysis. And it kind of offloads or outsources the thinking about what the types are, what the allowable values are for columns, what the properties of the data frame are, and it offloads that to Pandera. A roadmap item here that'll make the library more powerful is to extend parsing functionality to support arbitrary transformation. So this looks a lot like the Pydantic model. There are slight differences, but basically these parser decorators will apply to the corresponding attribute and then pre-process the data before passing it into the validation constraints. Principle 2 is to make schemas reusable, adaptable, and portable. And what I mean by reusability is once you've defined a schema, you can use it anywhere. So you can use it in your source code, you can use it in your test suite. And in this case, my test reduces to an execution test because clean data will always validate the output. And so now all the assertions happen at the schema level, Pandera schema level. By adaptability, I mean that inheritance semantics here apply to schema models. The classic vanilla version has its own way of adapting schemas, but here I can define my input schema, I can inherit from it, and thereby kind of communicate what a function in between these two should do to give you valid data. So here we can read here that there's this categorical one-hot field whose alias is one underscore hot underscore. And by giving you regex equals true, I can basically select any column starting with one hot and apply validation rules to that. So that makes things super concise. And now if I want to featureize the data for some kind of downstream like modeling, I can, again, focus on the actual computation needed to get from one form of data to another by giving this input schema for the clean data input. And now featureized data outputs this output schema. And so now I have type safety around the functions that I write with Pandas data frames. So that's pretty neat. And finally, for portability, there are so many data frame libraries out there. There's different schema specifications. So this is coming out in a release that I hopefully will release very soon. but it's frictionless schemas. So if people are familiar with the frictionless data table schemas, one contributor wrote a parser to get frictionless schemas into Pandera schema format, and there will be a round trip. So this is from Pandera to other schema specifications as well. So roadmap items are to decouple Pandera and Pandas type systems. So if we want to get to support things like Dask and Modin and other data frame-like data structures or libraries, we need to do this and also abstract out the validation and parsing logic to support non-Pandas data frames. And finally, add some things like titles and descriptions to make the human readability of schemas a little stronger. The third principle is that generative schemas facilitate property-based testing. So if I have the schema, I've taken a lot of trouble to write out all the metadata associated with my data frame type. Why not generate data for testing, right? So I can generate examples of whose size I can specify here with the size argument, and generate data in my PyTest suite. So under the hood, this input schema.strategy method will kind of compile all the statistics, the schema statistics, into a hypothesis strategy. Hypothesis is this property-based testing library that is amazing. So I've been using that a lot. And you can feed the schema strategy into your test featureized data function, and voila, you have clean mock data, and you don't have to handwrite mock data frames for testing anymore. So that's something that is really neat as well. Generative schemas also serve as multi-purpose artifacts, right? So at runtime, they enforce the types of your data frames. But at test time, as you can see, you can basically modularize and isolate your units of test to generate the data needed to test those functions. Some roadmap items here would be to add a global schema level override strategy, support data synthesis for joint distributions, which is fairly complex, but I think possible for simple cases. And then to make hypothesis strategies more efficient. So there are a lot of things in these issues that are not fully specified, but if any of these interest people, I'd suggest checking them out. And finally, principle 4 is to profile data and data pipelines. So this is this principle leads to a lot of things that haven't been developed in Pandera yet. But currently, you can infer a schema given some realistic data. Obviously, this isn't realistic data, but you can call infer schema, and it'll give you a schema object for you to start with. And you can write this out to a Python script. This is the vanilla Pandera schema syntax. And you can write it out to a YAML file. And a roadmap item for this is, we're basically data profiling, right, to produce a schema. So why not use a library like Pandas profiling to pull the metadata that it collects and then convert that into a Pandera schema. In terms of profiling data pipelines, if we have Pandera schema annotations, type annotations like this, presumably, theoretically, you could create a data flow graph. And then you can collect coverage statistics of schema annotated data frames, maybe a test time, and it could give you like a report of your data test coverage for at least your data frames. And it could point things out like how many test errors were produced when running the unit tests. This is at the early design phase, so a lot of this may not actually pan out. So roadmap items for this principle is to parse schema-decorated functions to construct a data flow graph, implement a better way of aggregating errors, and maybe a CLI for pipeline profiling and reports. I'm working on a PyTest Pandera plugin with tighter integration with PyTest, so you can check that out if you're interested. This is just a big table summarizing all of the roadmap items in the principles underlying them. And if you want to learn more, you can check out my previous talks and posts on Pandera. And yeah, this has been really like, this started off as a project to scratch my own itch. And I've been happy with the community has been slowly growing. You can check out the repo and the documentation and contributing guide. So if you want to contribute, I'll be around for the Americas mentored sprints session that'll happen tomorrow. And shameless plug to if you want, also you can contribute to the project by tossing a coin to your maintainer. And finally, just a shout out to PyOpenSci. This project started in around 2019 with very little usage, but once I submitted a proposal to PyOpenSci to like get this reviewed by the PyOpenSci community, it really helped me tighten up my documentation. At the time, it was only really me working on the project, and now we have a couple dozen contributors and a lot of people. The growth has been each uptick in this corresponds to either SciPy or PyCon or something, some kind of conference. So I'm really happy that people are starting to use this on a daily basis now, and yeah, I'd be happy to chat with you in the panel.
Thank you so much, Niels. That was super interesting, and I'm sure people will have a bunch of questions later for you. Thank you for the invitation for contributions as well. I think that goes for every project. People are always looking for stuff to do, and there are always so many issues, like people were saying in the chat. So feel free to reach out. I think we won't have time to any questions right now, so I just want to end the session so that we can get our break and be back in a few minutes with the panel sessions. So let me just, first, as I share my screen, I just wanted to give a big shout out to RK, our AirMeet host, who has been super helpful backstage. Thank you so much for all the technical help. And can you all see my screen? Is it working at all? Yes, okay. So I just want to thank all of our amazing speakers and for a great set of presentations. All of them were extremely interesting, and I can't wait to hear what they have to say at the panel later. So thank you all so much. So just as a reminder, at these times, so 10:30 PDT, 12:30 CDT, 1:30 EDT, and 2:30 PM BRT, which is where I am in Brazil, we'll have our panel discussions with the maintainers. So here are a couple of things we plan on talking about. So how to get started in open source, maintaining an open source project and avoiding burnout, building an open source community, the questions around privilege and open source as paid work and volunteer work and how that goes, questions about open source in academia, and how to become part of a core team of a project that you're interested in. So please join us later for our continuing discussion. Thank you all for your great questions. All the questions that were not answered are noted for later, and keep thinking about good questions for what we have later. So thank you so much. We'll close the session now for our break, and we'll be back in around 13 minutes. I hope I can see you later. Bye, everyone.